Hello, in this video we will look at operating system security. Now, security as such is become extremely important in this current world because systems as such are always connected. As a result, it becomes very easy for malicious programs to enter into the system. Therefore, operating systems should be designed in such a way so as to prevent as much as possible any loss of information due to such malicious intrusions. So, we will see a brief introduction to operating system security in today's video. So, whenever we design a system, we need to have some security goals, and these goals are the secrecy, integrity and availability of the system. Now, secrecy or confidentiality means that certain objects should not be visible to particular processes. For instance, depending on the privilege of a process and also on the privilege of the user running that process, certain objects like certain files stored in the disk or certain network sockets should not be readable by that process. Essentially, what confidentiality achieves is that unauthorized disclosure of some objects should be prevented. What secrecy or confidentiality achieves is that unauthorized disclosure of certain objects like files and sockets should not happen. With respect to integrity, means unauthorized modifications. In other words, a malicious user or a user with not sufficient privileges should not be able to write to a particular object such as a file or a socket. To take an example, a normal user in the system should not be able to modify some system related files. Availability, on the other hand, means that a particular user or a particular process has a limited use of the system resources. In other words, one particular user should not be able to hog the entire system resources. If such a thing is not available in the system, it could lead to what is known as denial of service attacks, wherein some malicious programs running on the system will prevent any other program which is present from having access to certain hardware resources like the CPU, the RAM or disk. So, availability in a system largely depends on how the operating system gets designed. For instance, we had seen how CPU schedulers can be designed in order to ensure fair scheduling. That is, every process in the system gets a fair share of the CPU depending on its priority. Now, in order to achieve secrecy and integrity, what operating systems generally do is to have access control. So, we will be looking at access control techniques in this particular video. In order to achieve access control, what it means is that every access to an object such as a file, a socket or it could be a hardware device like a printer or a monitor should be controlled. Essentially, if a process wants to get access to a particular file or any other object in the system, it has to go through an access control mechanism. Essentially, all and only authorized accesses can take place. In other words, if a process needs to access an object, then it definitely should be given access to that particular object. So, what we mean by access? Essentially, by access we mean an operation on the object which a particular process intends to do. So, these operations could be one of read, write, execute, create or delete. Now, this access should be permitted if and only if the particular process is authorized to make that access. In other words, only if a process is authorized to execute a particular program or read or write to a particular file, only then should the operation be permitted. In order to develop an access control system, there are three components: security policies, security model, and security mechanism. Now, security policy are high level rules that define the access control. Now, security model is a formal representation of the access control security policy and its working. Essentially, this is a formal model or a mathematically represented model of the security policy, and this model is used to help in proving various things about the system. For instance, you could use this particular security model to prove that a particular system is secure. Now, security mechanism is low level hardware or software that has the functional implementation of the policy, that is the security policy, and the model. So, in other words, you can think of this as a high level rules that define the security policies or the security features that need to be supported by the system. This is a mathematical model or a slightly lower level representation, and while this mechanism is the actual implementation of the policies. So, let us look at each of these more in detail. So, security policy is essentially a scheme for enforcing some policies within the system. So, how do we decide upon what policies a system should have? This is defined by what threats are present in the system, as well as how the system is designed. So, developing a security policy is not easy. So, it would require a lot of brainstorming to actually identify what are the various threats that, or what are the various attacks that are possible on the system, and once these attacks are known, then policies are created in order to prevent such attacks. So, how is the security policy actually look like? So, a security policy essentially would be a set of statements. These statements should be extremely succinct and precise, and should have the goals of the policy. So, these goals should be agreed upon by either the entire community or the entire set of people who are developing that system, or by certain top management, and this forms the basis for the security model, which is the formal mathematical representation of the policy. So, let us take how a security policy should not be written. So, what we are seeing now is that security policies are not necessarily for computer systems, but it could also be for organizations. So, this particular security policy is for this particular company called Megacorp Incorporated. So, the security policy is extremely short. It has just 4 statements, and it reads as follows. This policy is approved by the management. All staff shall obey this security policy. Data shall be available only to those with a need to know. All breaches of this policy shall be reported at once to security. So, what is the issues with this particular security policy? So, if we actually take a more closer look at this policy from this particular company, what we see that there are a lot of flaws in this. So, essentially the policy is not complete and cannot be used to build a security mechanism. So, for instance, this policy is approved by management, the first thing. So, typically in a security policy, the approval of the policy should not be part of the policy document itself. Second, all staff shall obey. So, what we mean by this? who enforces that a staff should obey? Is it a moral requirement of the staff to actually obey to this policy, or there is actually a unit which enforces all staff in the organization to obey for this particular policy? Third, the need to know. So, how do we define what a need to know? Who determines who should know what information? So, this is not specified or not very obvious from this particular policy statements. Finally, all breaches of this policy should be reported at once to security. So, how are breaches detected? The security policy does not tell anything of this form. Whose duty is it to report them? So, this too is not mentioned over here. So, as you see, even though this particular policy is very short and very terse and incorporates just 4 points, still it leads to a lot of ambiguity, and such ambiguity would lead to a weak security for that company. So, when we have to write a security policy for a company, it should be complete in all aspects. Now, let us look at the security model. Essentially, why do we need to have the security model at all? Why can't we go from the security policy, use the security policy and directly implement security mechanisms? Why do we need to have a security model present in this entire hierarchy? Essentially, by having a security model, we are able to model the security policy in a lower and more formal construct. So, in this way, any gaps in the security policy would be detected. And secondly, we could also use tools and techniques in order to argue or prove that the system is indeed secure with respect to the security policy that was defined. So, the last aspect is the security mechanism. So, security mechanism, as we have seen, deals with implementing of the security policy. Now, it is important that implementing the security mechanism is bug free. It has no bugs. Why is it extremely important that there are no bugs? This is because if there are bugs in the implementation of the mechanism, then it would be possible for attackers to exploit that bugs and getting unauthorized accesses into that system. Second, the implementation of the security mechanism should be the trusted base. Essentially, this is the core from where the security of the entire system would depend upon. Therefore, if it itself is buggy and incomplete, it will not create a secure system. So, properties of the security mechanism implementation is that it should be tamper proof, non-bypassable, and by non-bypassable we mean that all accesses into the system should first be evaluated by the security mechanism. Then it should be a security kernel. So, what it means by this is that the entire implementation for the security policy should be confined to a limited part of the system, and it should not be scattered into various parts of the system. So, having a security kernel where everything is just confined into, say, a small part of the entire system would make it easy to test and debug and verify in terms of security. Again, it should also be small. So, a small size for the security mechanism will ensure that it can undergo some rigorous verification. Now, there are 3 techniques for access control. They are the DAC, MAC and RBAC. So, DAC is the discretionary access control, MAC is mandatory access control, and RBAC is role based access control. So, we will be looking at the DAC and MAC in this particular lecture. Discretionary access control, or DAC, is an access control which is based on the identity of the requester. There would be a set of access rules, what requesters are or not allowed to do. So, these access rules would define essentially what objects the requester, also known as a subject, could access, and what objects could be read, written to, executed, created or deleted, and so on. Now, the privileges for these various objects are granted as well as revoked by the system administrator. So, users, if they have a particular privilege, then they can also pass on that privilege to other users. A very common example of a DAC system, that is a discretionary access control system, is the access matrix model. So, the access matrix model was designed by Butler Lamson in 1971. It comprises of subjects and objects. In addition to this, it also has a table in this form where each cell has some particular actions. So, subjects are active elements in the system, such as users of the systems or processes or programs that are requesting information. Objects, on the other hand, are passive elements which, for instance, store information. Now, the actions are specified in each cell of this particular matrix. So, for instance, the subject Anne has execute permissions for program 1, she has read and write programs permissions for file 2, and she has read and write permissions for file 1, as well as she is the owner for file 1. So, if you look more carefully, Anne does not have any permission on file 3. She can neither read it nor write it, nor can she actually read or write the program 1. So, in order to represent this access matrix model in a formal method, what we can do is define this matrix A, which comprises of XSI, that is for subjects, and XOJ, which is for an object. So, A of this particular thing would indicate the subject SI, for instance Bob, and an object, for instance file 2. Then we could also give rights to each cell in this particular matrix. For example, the rights could be taken from a set like this R1, R2 to Rk, and this particular thing A of XSI, XOJ is a subset of R. So, for example, the rights in this example is own, read, write, execute, so on, and these would be in the set R, and corresponding to each cell in this matrix we define what the rights are. So, this would define what the right for subject SI has on the object OJ. In addition to this, there is something known as the primitive operations. So, these is represented by O, and it is a set of 6 operations which is specified here. So, this is, for instance, enter R into some location in the matrix or delete R from that location. Here R is taken from the generic rights. So, it is an element from the set R. Similarly, other operations are to create a particular subject XS, create an object XO, destroy a subject XS, or destroy an object XO. So, these are the only primitive operations that can be done on this particular access matrix. So, as we see, each of these primitive operations could either modify the contents of a particular cell in the matrix, or it could delete an entire column with the destroy subject and destroy object. So, it could either delete a particular column or a particular row, or if it wants, it could also create a new column, that is creating an object or creating a subject. So, once we have defined such primitive operations, we can define something which is a bit more complex and based on these primitive operations which are known as commands. So, to recollect, we have the access matrix which is specified by A, we have the generic rights R1 to Rk, and we have 6 primitive operations as we specify here. So, we can use all of this to create complex commands like this way. A typical command would look like this, and it would be called, say for instance, alpha, which takes several parameters x1 to xn, and we can have a set of rules. For instance, if R1 is in this matrix cell and R2, R3 and so on, then perform these following operations. So, what we are seeing is that based on these low level primitive operations, the generic rights and the access matrix, we can have more complicated commands on the access matrix. So, let us take a few examples of such commands. For instance, create process comma file. So, process here is the subject, and what it means to say is this process wants to create this file. So, the command will work like this. So, first we use the primitive operations, create an object file, and then enter own into that process comma file. So, this process comma file corresponds to the cell in the access matrix. So, if this particular command is not present, then it will not be possible for a process to actually create a particular file. So, this is a very simple example. So, we could have something a bit more complicated like this particular example, that is confer R, owner, friend, file. So, owner and friend are the subjects and file is the object over here, and what is intended to do by this particular command on the access matrix is that we want to confer right R, which is present over here, to a friend for that particular object. So, this owner wants to confer the right R for the friend with respect to this particular file. So, what goes on in this particular command? So, essentially we first test if the owner is indeed the owner of that file. So, we see that first, if own right is present in owner comma file in the matrix cell corresponding to owner, the subject, and file, the object. If this is indeed true, then enter R, that is enter the right R into the friend comma file part of the matrix. Similarly, we can have another example where we can remove a right from an X friend. We are passing this particular command 3 parameters, the owner, X friend and the file. So, essentially what we want to do is revoke the particular right R from this X friend, which is another subject. So, the command looks like this: if own is in the owner comma file, that is if owner is indeed the owner of the file and the right R is present in X friend comma file, then delete R from X friend comma file. Therefore, we can remove the right R, which could be a read or write or execute right, on the file with respect to X friend. Essentially, the X friend subject will not have the right R on the particular file. So, a protection system, if we actually represent it by this particular matrix, and what we have seen is that we could apply commands to it, like we have seen a couple of commands in the examples in the previous slide, and with each command we are modifying this particular access matrix. So, this command for instance has modified this cell over here in the access matrix. Similarly, if you run another command, another part of the access matrix or multiple cells in the access matrix will be modified. So, based on this we define what is known as a leaky state. A state of the access matrix is said to leak a right R if there exists a command that adds the right R into an entry in the access matrix that did not previously contain R. So, what this means is that we have the state of the matrix here and we run a command, and as a result there is an R or write R which is entered into this particular matrix. So, what we say is that this particular state of the matrix leaks R. Now, a leaky state does not always need to be bad. So, it is meant to left to us to actually determine whether leaking this R from a particular cell in the matrix is good or bad with respect to security of the system. So, let us define when a system is said to be safe. So, we have two definitions of safety. So, the first definition, so a system is safe if access to an object without the owner's concurrence is impossible. Second, a user should be able to tell if giving away a right to a particular subject and with respect to an object would lead to further leakage of that right. So, let us see what this means from a formal model. Suppose a subject S plans to give another subject S prime the right R to object O. Okay. With R entered in A S prime comma O, that is with the new right added to this particular cell of the matrix, is it possible that R could subsequently be entered somewhere else in the matrix A? If such a thing is possible, then the system is said to be unsafe. So, essentially a system is unsafe if any operation or any command run on the access matrix could result in that particular right being conferred or transferred to someone else or to somewhere else in the matrix. So, we will look at an example of an unsafe state. So, let us consider these two commands. One is the confer execute. So, the subject S wants to confer the subject S prime the execute right for O. So, this command confer execute S comma S prime comma O states that a subject, if it is the owner of the object O, then it can give the right X, that it can give the right to execute object O to another subject S prime. Now, let us say our system also has this particular command which is called modify rights, which states as follows. If a particular subject has an execute right with respect to an object, then it can also enter a right in that particular object. In other words, what this modify right allows us to do is that if a particular subject can execute an object, then it can actually modify its rights in order to change the object as well. So, essentially it can write into that object. So, let us look at a particular scenario to see how this example shows an unsafe state. So, let us say Bob creates an application object. He wants it to be executed by all others, but not modified by them. So, the system is obviously unsafe due to the presence of the modify right in the protection system. Alice, another person who has the execute right for that particular object or application, could invoke modify right to get the modification rights on that application, and once Alice gets the right to modify that application, then there is nothing stopping Alice from actually changing that operation. So, what we see is that because Bob has given the execute permission on a particular object, and the system's policies or the system's access control mechanism is built in such a way that because this right is present in a particular object, then the W right is also given to that particular object. Essentially, if a subject has the execute right for an object, then that right is actually transformed and transferred, and it will cause the W right to be also associated with that particular object with respect to that subject. Therefore, this particular state in the system is an unsafe state. So, how do we actually implement the access matrix model? So, one way, as we have seen, is to have the matrix representation. However, the issue with this particular representation is that it is too large as well as it is too sparse. So, it is not a very efficient way to use. The other technique is to use something known as an authorization table, as is shown over here. So, this particular table is used in databases, and what it actually has is that each row comprises of a user, it has a right and it has an object. So, it says that, for instance, Anne has a read write on the object file 1. So, for every write that Anne holds, there will be a separate row in this particular table. So, the problem with this particular scenario is that, or this particular implementation is that one needs to actually search the entire table in order to identify whether a particular user has a particular right on a particular object. So, it again is having a lot of performance issues with respect to how long it takes to determine a particular right for a subject and object. So, another technique of implementing the access matrix model is by using capabilities. Here, each user is associated with a capability list indicating for each object the permitted operations. For instance, Anne for file 1 has the following rights over here. For file 2, she has these rights, and for program 1, she has these rights. Similarly, for every user, we have such a list, and these are the capabilities list for that user with respect to each of these objects. So, the advantage of such a model or such an implementation is from a distributed system scenario, since it prevents repeated authentication of a subject. So, essentially, once the subject authenticates itself in the distributed environment, then it could obtain this entire list, and the system will know its rights for each object which is present. However, the limitation is that it is vulnerable to forgery. If a particular right or a list is copied by an attacker, it can be then misused. A third way of implementing the access control model is by what is known as ACL, or access control lists. Essentially, each object here is associated with a list indicating the operations that each subject can perform on it. Essentially, this is the opposite of the previous way. So, corresponding to each object, we have a list, and each node in the list has a subject and the corresponding operations that are present here. So, the advantage that we get with this particular thing is that it is easy to represent by small bit vectors. So, if you look at how Unix actually implements this ACL, so we see that every file in a Unix system has 9 bits associated with it. So, this gives the authorization for each file to be specified. For instance, there are 3 bits which specify read, write, execute for the file, for the owner of the file. Then we have the group, we have the 3 bits RWX for the group, and for the rest of the world, for the others, that is, we have 3 more bits. Thus, in a Unix system which uses the ACL implementation of the access matrix, there are 9 bits involved, and each of these bits would give permissions to various users of that file. Now, The vulnerabilities in the discretionary policy is that it is subjected to the Trojan horse attacks. So, what we mean by a Trojan horse is that it is a small code which is present in a larger non-malicious code. So, this small Trojan present in the larger code is the malicious code. So, the issue with this is that because the Trojan is actually like a virus which is joined with a much larger program. So, the Trojan can actually inherit all the users or all the processes privileges. So, for instance, if you have a Trojan which is connected to, let us say, a program which has super user privileges to execute or which needs to execute as a root, then the Trojan itself would be able to inherit all the root permissions. The reason why this happens is that the Trojan present in the process would send requests to the operating system in the valid user's behalf. So, from the OS perspective, the operating system will not be able to distinguish whether it is from the valid process which is started by a valid user or whether the request is coming from a Trojan. Therefore, it becomes difficult to detect. Another drawback of discretionary policy is that it is not concerned with information flow. Anyone with access to information can also propagate information. For instance, if we have this one person over here who is able to read a particular file, there is nothing stopping this person from actually making a copy of this file and transferring it to 100 different people. So, as such, the discretionary policies do not take care of the flow of information from one person or one user to another. So, it is only capable of preventing access to information, but not the flow of information. On the other hand, in order to consider flow of information also, we need to use what is known as information flow policies, which restricts how information flows between subjects and objects. So, we will look at information flow policies in the next video. Thank you.